start the video. In this video, first part is gonna about ideal conditions of rockets. Just like there are some ideal working conditions of some machines. Like that only rocket working conditions of rocket had some ideal conditions. Okay, so whatever it is. So the first ideal condition in which rocket should follow, the fuel which is inside the rocket should be uniform everywhere. Now, what does it mean? It simply means, I'm just stating the obvious. Like gases are well mixed. No clumps of different gases of fuel. There should be no clump gases like all fuel oxidizer should be well mixed. No clumps, uniform composition. Like just like salt mixes in the water, fuel should mix in the oxidizer, homogeneous. All species of the working fluid treated are gaseous. Fuel is always treated as gaseous when it is studied in physics. Okay, confirm. Working fluid, this is just obvious now because in the previous slide I told you that fuel is gaseous, so it will follow perfect gaseous law. Okay, some a kind of real gas. There is no heat transfer. So what is it saying that the heat which is generated here, na, it is not transferred to the outside surroundings. Well, the process is kind of adiabatic. Heat can leak through the walls of rocket or be transferred to the surrounding, but assumption. But see, the thing is, we're talking about ideal conditions. Ideally, heat should not transfer outside the rocket, but sometimes, in real life, it does, right? It does. But we treat it that way. Or because on treating that way, the calculations of rockets become easy. And we'll see how. Mm. There is no applicable friction is not there. The walls, fuel is passing through the walls, right? Through the walls, friction is not there. And boundary layer is also not there. Simply is the friction between rocket gases and rocket walls are zero. This is one condition we assume while studying rockets or making calculations of rockets. Okay, there are no shock waves. Yeah, there are no shock waves. The smooth and continuous flow of gases. Simple. Hmm. As you can see, we are being too idealistic. That's why rockets does not work sometimes. Because the thing, see, while making rockets, the conditions are so like disruptive. If you take every factor, like rockets will have shock waves, rockets will have non-homogeneous mixture, rocket will have that, rockets will have that. The calculation will become so difficult, we will not be able to calculate anything. So that's why we assume idealism. And in that idealism, we mix reality. Not that in reality we mix idealism. In idealism, we mix reality little bit, little bit. Okay, we'll see when this series move forward how we do that. Just bear with me. Propellant flow rate is steady and constant. So what it is saying that mass flow rate is constant throughout the like rocket. Flow is smooth, steady, constant over time. Mass flow rate does not change. Well, with mass flow rate, like amount of mass flowing here is the same as amount of mass flowing here. As simple as that. Transient effects, startup and shutdown duration. See what happens during the startup. Like when rocket starts, there will be some fluctuations in anything. Like we neglect that. During shutdown also we neglect that. Shutdown is happening right now only because we have what reusable rockets thanks to Elon Musk. So startup and shutdown, whatever the effects are there, no, we neglect it for calculation purposes. Hmm. This is too much idealism. All exhaust gases leaving rocket nozzles. The rocket, see here also. Like rocket nozzle, like velocity of these exhaust gases should always be parallel with nozzle walls. No, no, nozzle axis, sorry, nozzle axis, whatever. Hmm. So that it maximizes the thrust. For maximizing thrust, the velocity of gas should be parallel to the nozzle axis. Chemical equilibrium. Another thing is the gases are mixed. The gases should be in chemical equilibrium here. I mean, there should be no chemical reaction taking place after the mixture of fuel and oxidizer. Why would there be? Chemical reactions are complete. In composition, gases does not change. Chemical reactions complete and composition of gases throughout change. Throughout doesn't change. It only expands. It is from the first point only the gases are homogeneous throughout the. Mm. Ordinary propellants are stored at ambient temperatures. Cryogenic propellants are stored at boiling points. So the ordinary propellants, like normal propellants, solid fuel, liquid fuels, are stored at normal temperatures. But the cryogenic propellants, like liquid hydrogen, liquid oxygen, are stored at their boiling points. Mm. Hmm. Hmm. Okay. So these are the ideal conditions of the rockets. Let's go through them once from start. Working fluid should be homogeneous. Gases should be well mixed properly. Okay. Working fluid is gas, so it should obey gaseous law. Okay. There is no heat transfer, no heat leaking outside the rocket through the walls. Okay. No friction between gases and the walls of rocket. No shock waves. Propellant mass flow rate is steady. It is steady flow rate, smooth and steady flow of fuel here. We assume. The startup and shutdown effects, whatever like unsteady effects it cause, these are neglected. All exhaust gases are firing parallel to the nozzle axis for the maximum thrust. Gas velocity, what was the gas velocity? Gas velocity, temperature, and density. How can they assume your gas velocity are gas velocity is constant throughout? Gas velocity is increasing now. I have too much idealism. But whatever, the book says it. Gas velocity, pressure, and temperature and density uniform across any section. Oh, sorry, I get it. So what they're saying is, mm, see, if you take a section here, na, what they're saying, the velocity, the pressure and temperature across this line are same. Density also. So obviously it will be, na. And if you know, on this line, the composition of gases, the velocity, the pressure, everything will be same. That's what they're saying. Just chemical equilibrium. Okay. Ordinary properties are so ambient temperature. Okay. Okay. So yes, I hope you got the what are the ideal conditions of rocketry. Okay, rocketry.